Again, you can also generalize this approach in a certain way. So this then leads to the so-called generalized mutual information, where you just replace these Shannon entropies by the corresponding Grignard entropies. That's quite straightforward and leads you to a whole spectrum of entropy. So it's similar to the spectrum of generalized dimensions. You can do this as well with the entropies. Or another very recent generalization of this concept was that you can also consider conditional probabilities. So what I've used here are just joint probabilities, but you can also consider conditional probabilities of sequences to be found in one system when you know a certain sequence has been found in the other system. So there is some sort of prediction approach involved in this case. And this leads then to the so-called transfer entropy, which you can interpret a little bit similar to the mutual information, but which gives you additional information about the direction of information flow. So whether it's one system that determines the evolution of the second one, or whether it's more, let's say, bidirectional interaction. So this you would not see by mutual information, but you can resolve this by this transfer entropy. So that's the idea. Okay, to give you some idea of the mutual information, once again, you know this slide already, the time series of daily air temperatures from Tokyo. And what we have done here is comparing the behavior of the simple autocorrelation function and the mutual information function for this series. And what you see is basically, okay, if I remove these seasonal components, the behavior is pretty much the same. So, which is not really surprising, because when you have linear correlations in your system, these linear correlations are also detected by the mutual information, because linear correlations are just one type of statistical dependence. On the other hand, you can have the case that you have no linear correlations, but your mutual information shows that there are some statistical dependencies. In this case, they cannot be linear ones. So that's the major benefit of this particular measure. And I will show you some animation. So recurrence is a fundamental feature of nonlinear systems, which has been introduced by Poincaré almost 120 years ago in context of celestial dynamics and stability of planetary motion. I like it very much. And the idea is that one considers, in this case, an embedded version of the time series. So we take a sequence of, in this case, 3 subsequent values of the time series as an embedding, and look how does the system behave in this 3-dimensional space in this case. And what you will see in some seconds is that there will be some sort of chaotic attractor forming, which is related to this Lorentz attractor I mentioned earlier today. And you will see a bit the structure of this system. Okay, it looks like this. And now, what is a recurrence? Recurrence is that I pick just one point on this trajectory and I look for neighboring points of this trajectory which have been observed at other times. So for example, I take this point and I find that there are 3 other points which are similar in that sense. And I mark these points by ones in this R or recurrence matrix and by black dots in this so-called recurrence plot. So the black dots in this plot just correspond to the ones in this matrix, and the white points correspond to the zeros. So where different observations are not very similar. Okay, it will go a bit faster very soon, and you will see that there are certain structures which emerge in this representation. Yes, and in particular, these diagonal lines are interesting because they correspond to intervals where the dynamics of the system is quite similar to the dynamics in former time intervals. Yes, and what one can do now is considering these diagonal lines, for example, for reconstructing the attractor. So that's one specific approach, which is quite new, by the way, that one can do reconstruction of the dynamics just based on such a recurrence matrix. But more interesting is what you will see in a minute, to do statistics over the length of these diagonal structures. So that's what you will see here. So there are some very long diagonals. Then there will be some shorter diagonals. Here, these two. And they're more even shorter. And what you will see is that there's then some histogram of the length of these diagonal lines, which you can use for quantifying the dynamics of your system as well. So this will run now. You see that there are many short diagonals, only a few longer diagonals, and from this histogram we can compute so-called measures of complexity, which characterize as the dynamics of the system. So this approach is, by the way, also called recurrence quantification analysis in this case. So there are only some examples: recurrence rate determinism, mean diagonal length, entropy. You do not need to remind them in all detail. The point is that you should know that there are some quantitative characteristics you can define based on the distribution of these diagonal structures, of the length of these diagonal structures, which tell you about the predictability of the system. Yeah, and here are some examples. For example, when you have a completely stochastic system, you have a very diffuse picture. You basically see no structure in this recurrence plot. So if you have such a plot, you would immediately see it must be a stochastic system. In this case, you have a chaotic deterministic system, and you see that there are some structures which are quite interrupted, but there are some diagonals, and this indicates that there is deterministic dynamics in the system. Okay, just once again, the three different possibilities. So when you have a periodic function, like a sine function, you will just find diagonal lines. And these diagonals correspond to the different periods of this sine function. So it's quite easy to see when I have a sine function, after a period that corresponds, after a time that corresponds to the period of the sine function, I will approach again the same values, and by this I get some diagonal line in this plot. So the distance between, sorry for this, the distance between these diagonal lines is also just a measure for periodic behavior in a time series.